Okay, hi folks. Well, we'll see how this works out. It's had a little trouble staying focused, but hopefully it'll work well. These videos are going to have to be broken up a little bit. It's a 2 gig card in the camera, so we'll be doing shorter videos, trying to concentrate on a topic, and then move on to a new video with a new topic. So the first one, this is a carryover from Thursday's class. At the end of class, we were talking about the geometric and the negative binomial distributions. Remember, these are discrete distributions, and as far as what we're looking at here, in both cases, we're looking at the number of trials needed to get a specific number of successes. In the case of the geometric, remember that we were looking at one success, and in the case of the binomial, we're looking at some general number R of successes. So as far as the mass functions from last time, as a reminder, for the geometric, we had p of x is equal to p times q to the x minus 1. And that was for x equals 1, 2, 3, and so on. And for the negative binomial, the mass function was x minus 1, choose r minus 1, times p to the r times q to the x minus r. And remember that x starts at r, goes r plus 1, r plus 2. And I think I just went off the board. Or at least off the screen. So don't have much space to work with so that we can try to keep this focused. So, okay, so as we did with the binomial, the first thing that we're going to do is take a look at an applied example here where we're getting values of r and p in this case and calculating some probabilities. So, as far as this one's concerned, you may be familiar with a game show called Minute to Win It. In order to win the biggest amount of money in this game show, what you have to do is you have to complete a series of fun little odd tasks. And each time you complete one, the amount that you've won goes up. And basically, it's in a way like baseball because you're granted 3 strikes. And on the third one, the third time you fail to complete a task, you are out of the game. So it may be that you have 3 attempts at the same task at one point in time, or it may be that your 3 misses occur on different tasks. Okay. So let's just say for the purpose of this, we're going to say that 40% of all tasks are completed. And you may be thinking that at this point p is 0.4, but really it isn't, because what's going on is that you move out of the game when you don't complete a task. So for our purpose in this game, we're going to work with a value for p of 0.6. 60% of the tasks aren't completed. So for our first setting here, what we're going to get is the probability that the first failure occurs in the fourth round. So in this setting, what we're saying is that on the first three tasks, the person or the players got through the tasks successfully, and then on their first attempt at the fourth task, they ended up failing to be able to complete it within that 1 minute period. So as far as this is concerned, x is equal to the number of tasks until the first failure. So this is that r equals 1 scenario, and hence we're going to use the geometric. So in this case, we have p of 4, which is equal to 0.6 0.6 for the, dang it, I wish I could push that button. You're loving this right now. It's 0.6 for the one failure, the 60% of the time that they don't successfully complete it. And then 0.4 cubed, each one of those for the 3 rounds or the 3 tasks that were successfully completed. And if you calculate that out, you get 0.0864. Now, for a negative binomial case, remember that in order to end the game, it occurs when somebody fails for the 3rd time. So let's say that what we're looking at here is the probability that the person is out of the game on the 9th attempt. Out of the game means they haven't completed a task 3 times. So basically, if you want to think about it in terms of the game, they managed to get through the first 6 tasks, and then the last failure occurred on the 7th task. It may be that they failed to complete the 7th task on any one of the tries, or it could be that 2 of the failures occurred somewhere on the 1st through the 6th task. Again, as far as we're concerned here, p is 0.6, and we're looking for the probability that x equals 9. This is that negative binomial. So we have 8 choose 2. That's the number of ways that in those first 8 attempts there were 2 failures. We have the 3 actual failures on the different tasks. So we have 0.6 cubed, and as I said before, they were able to successfully complete 6 of the tasks, so we have 0.4 to the 6th. And if you multiply all of that out, you get 0.02477. Now, the one more extension of this we're going to do is, here we said the person is out of the game on the 9th attempt. We're going to change this to person is out of the game by the ninth attempt, sorry, not by the ninth attempt, on or before the ninth attempt. So in this scenario, it could be the fact that on the first task, they failed to complete it in any of the 3 attempts and they didn't win anything, or it could be that they ended up getting through a couple of them before they failed for the 3rd time, but at most they got through 6 of them. So as far as we're concerned here, this is the probability that x is less than or equal to 9. That's going to be the sum from x equals 3 to 9 of x minus 1, choose 3, times 0.6 cubed times 0.4 to the x minus 3. So to give you an idea, if we were to start writing this out, what we would have when x is, x minus 1, choose 3, my goof. This is x minus 1, choose 2, not choose 3, because we know that the last one has to be their last failure to complete a task. So these are the first 2 failures to complete tasks. So if we start writing this out, we've got 2 choose 2 times 0.6 cubed plus 0.4 to the 0, plus, times 0.4 to the 0, plus 3 choose 2 times 0.6 cubed times 0.4 to the first, plus 4 choose 2 times 0.6 cubed times 0.4 squared, all the way through 8 choose 2, 0.6 cubed, 0.4 to the 6th. If you do all the arithmetic for that, what you end up with here is 0.758965. So based on this model, about 24%, around 1 out of every 4 contestants would make it past the 6th round. Now, as you know, the binomial function is on your calculator. Both the binomial PDF and the binomial CDF are on there, so you can go ahead and do those calculations that way. The negative binomial is not on the calculator, so you'll have to punch those in. As far as the geometric is concerned, you can see it's just p times q to the x minus 1, so even though there's a function on your calculator for it, you're going to spend more time punching things into the function than you would actually calculating the value just by punching the individual numbers in and using the exponentiation key. Now that said, we've talked about CDFs, and in some cases, like the binomial, there is no nice formula for the cumulative distribution function, but as it turns out, for the geometric, it is rather nice. So right here we've got the CDF of a geometric. So we're looking for the probability that x is less than or equal to little x. Remember that this is a discrete random variable, so we're summing here. So So as far as this is concerned, we're summing from t equals 1 to x of p times q to the t minus 1. And you might recognize the fact that this is a finite geometric sum. So we're using the geometric series information. But since we're not going to infinity here, in a lot of cases it's actually easier to use the complement. So if we look at the probability that x is greater than little x, then what we're going to have here is t equals x plus 1 to infinity of p times q to the t minus 1. And if we start writing this out, what we recognize here is that we have p to the x, we have p times q to the x plus p times q to the x minus 1 plus p, I'm doing really well here, sorry. Let's try that again. P times q to the x plus p times q to the x plus 1 plus p times q to the x plus 2, so on. We can factor out p, that's in common here. And then we have q to the x plus q to the x plus 1 plus q to the x plus 2, and so on. So we have a geometric series here. So what we have there is p. The first term in this series is q to the x. And the common ratio is q. Remember that 1 minus q is p, so we'll have p divided by p. Those are going to cancel. And what we're left with here is q to the x. There's a logical explanation for this, because what this is saying here, or asking, is what's the probability that we have to do more than X trials to get the first success? Well, if it takes more than X trials to get the first success, everything that preceded it must have been a failure. So this is the probability of the first X trials all being failures. So going back to the CDF, if we want the probability that x is less than or equal to x, this summation here works out to be 1 minus q to the x. Now, the last piece in this is to talk about a special property that the geometric distribution has. And we just said that the probability that x is greater than some number, we'll just call that a, would be equal to q to the n. So the question that we're going to look at here is the probability that x is greater than some quantity a plus b, given that x is greater than a. What we're looking at in terms of words is given that we have had more than A trials, what is the probability that our first success comes after A plus B trials? Should move my tape. Okay, so we'll get rid of this question here and get to the probability calculation. So this is a conditional probability. We're using the same techniques we used back in chapter 2. So this is the probability that x is greater than a plus b, intersected with x greater than a, all divided by the probability that x is greater than a. So we have the intersection up here. X is larger than a plus b, x is larger than a. In order to satisfy both of those, we're assuming that b is positive. So in order to satisfy both of those, x has to be larger than the larger number. So the intersection is x is greater than a plus b. So this becomes the probability that x is greater than a plus b divided by the probability that x is greater than a. We can now use the formula we developed up here. And this becomes q to the a plus b divided by q to the a. We'll cancel, and this works out to be q to the b. But if you relate that back to the formula we started with, this is equal to the probability that x is greater than b. So, effectively what this property is saying is, as far as the geometric distribution is concerned, all of these failures that we've had beforehand have no impact on the number of trials that it takes us from here on out to get to our first success. And this property that the geometric has is referred to as the memoryless property. The geometric is the only discrete distribution that has the memoryless property. There is one continuous distribution we'll get to in chapter 4 that also has the memoryless property. And we'll talk about how these two distributions are related to each other when we get to that point. But to just slap some numbers in here, what this is basically saying here is, suppose we were interested in the probability that x is greater than 10 given that x is greater than 3. So we've already had 3 failures, at least. What's the probability that it's going to take more than 10 trials in order to have our first success? This is equal to the probability that x is greater than 7. You would plug your appropriate value of q in, and you would raise it to the 7th power. Sorry, I had to see how much time I had left. Okay, now, at this point, we've got to deal with the mean and the variance the same way we did in the case of the binomial. So we're looking at the mean, variance, and standard deviation of a geometric, random variable. For e of x, what we have here is the sum, x equals 1 to infinity, of x times p times q to the x minus 1. When we did this with binomial distribution, we had some canceling that we could do. We had some rearranging that we could do that would allow us to get something that summed to 1, and a lot of stuff dropped out. That's not the case here. We don't have anything we can cancel, so we have to look at some other possibilities. Now, the one thing that pops out right away is the fact that this summation is over x. So as far as we're concerned, the term p is not a function of x. So we can certainly pull that outside the summation. So we have p times the summation of x times q to the x minus 1. Now, as far as this is concerned, if you look at x times q to the x minus 1, it may actually look familiar to something that you saw in Calculus 1. X times q to the x minus 1 is actually the derivative of a function. It's the derivative of q to the x. The question is, when you're taking the derivative, what are you taking it with respect to? Well, if it was d dx, then essentially we'd be saying we're taking the derivative of an exponential function, but that's not it. This is a power function where we want the derivative to have the exponent come down as the coefficient and then reduce the exponent by 1. So this is the derivative with respect to q. So with this, what we're going to do, notice I put an arrow, not an equal sign, is that this piece right here now becomes p times the sum x equals 1 to infinity of d dq times q to the x. At this point, a lot of people just kind of go, okay, now what? And the fact is that the math that allows us to do this is stuff that's basically covered in real analysis, and since not everybody's had that, we have to do a little bit of hand waving here. But basically, under certain conditions, it is possible to switch the summation and the derivative, to switch the sum and effectively the limit. So in this situation, that switch is allowed, and so what we end up with is p times d dq times the sum x equals 1 to infinity of q to the x. We have a geometric series here, so certainly we can do something with this. So we have p times d dq. The first term in the series is q to the 1. Q there. Common ratio is q, so we have q over 1 minus q.